Can everyone see the screen? Yes.
The slide, the talk itself, can everyone see that?
Yes.
Okay, great. So, good day, good morning, and good afternoon to everyone. I'd first like to thank the organisers for allowing me to speak to you today about my work. I'm going to be looking at the screen here, so I won't be looking exactly at the camera. So that might be, if you're wondering why I'm not doing that, that's why. And so today I'm going to be talking about, can I highlight? That's right. Transformations of summary statistics from linear mixed model association on all or none traits to the odds ratio. So if you're wondering why I used the phrase all or none, that's a kind of a tip of the hat to some papers published back in the 70s by Robinson, where they were looking at the liability threshold model and kind of studying all or none traits. So I thought I'd kind of put that in the title as a little bit of a historical mark. And I'd also like to thank Peter Vischer and Jan Jan for sharing this kind of concept with me, because it was quite a strange principle when Peter first presented it to me, but then once I got into it, it was very interesting. So what's the motivation? So we have a linear mixed model methodology is becoming more useful, or is becoming more prevalent for GWAS. And the reasons are is that it can be used to correct for population structure and cryptic relatedness, and has been shown in many papers to be more powerful. So probably more classically, it's used in the animal science, or it came out of the animal science and plant breeding literature and moved its way into the human genomics literature, and probably has been used mainly to characterize genetic variation in complex traits, but recently has moved towards large-scale GWAS of complex disease traits. So where they just use the linear mixed model, but plug the phenotype in as 0, 1. And so these papers here that I cite are kind of examples of that. So the interesting question, though, that comes out of that is that when you apply the linear mixed model, or the linear model for that matter, to all or none traits or to dichotomous traits, the genetic effects are on the observed 0, 1 scale. And so the problem with that is that it's not directly comparable to estimates from logistic regression. And then, so if you have a variety of studies that use different models to analyze the data, then the effects are kind of not comparable across those studies. So the odds ratio for those who study disease traits is often a common measure used for the strength of association of a genetic effect. And the nice thing about it is it's not affected by case ascertainment. It's kind of a data neutral measure of the association. So you may want to think about, if you estimate the effects on using a linear model, how would you get back to the odds ratio? It's probably a natural place to try and get back to. So I thought I would express that problem in a little data example here. So here I'll introduce some notation where I call big K the population prevalence of the disease, and little k here the sample prevalence. So in this simulation, or this conceptual example, we've oversampled the cases relative to the population prevalence. And we have 3 variants, SNP1, SNP2, SNP3, and here are their allele frequencies, and I've gone away and simulated a phenotype under the liability threshold model with these parameters here in GCTA. So if you're not familiar with GCTA, that's the software used and developed by Jan Yang within this group that I work within. So here you can see that the logistic, the effect from the logistic model looks like this. And then we have the effect from running the linear mixed model in GCTA as well. And so these effects here are difficult to compare. So it's easy when in logistic regression to transform the effect to the odds ratio by simply taking the exponential of the effect, and you get the odds ratio. And it has a kind of nice interpretation within the logistic regression framework. The problem is that the conceptual problem is, how do we transform these effects to the odds ratio? And so that kind of motivates our goal. So the main main kind of purpose of this piece of work is a utility piece of work. We're not kind of trying to forge new grounds in understanding statistical genetics per se, but we hope that this would be useful to a lot of practitioners who analyze these data and trying to compare results from different studies. So we seek a transformation between the estimates of the genetic effects from the linear mixed model to the odds ratio using only summary statistics. So the final kind of phrase is important, where summary statistics really will limit how we do our mathematics. And I've kind of already stated this, but just to kind of put the goal in bold. Now, I wanted to kind of introduce, although these concepts probably are quite simple to those who have studied disease association, I wanted to put this kind of mathematical warm-up in there to kind of get a feel for some of the notation. So here I denote this mathematical P as the probability, and the odds of an event occurring is just the probability that the event occurs divided by the probability that the event doesn't occur. And then we can express the odds ratio as kind of the ratio of the odds of the event given the exposure over the odds of the event given the lack of the exposure. So the odds ratio is kind of interpreted or looked at when we have this, these conditional probabilities, which are often can be expressed in this 2x2 table here. And so this 2x2 table is kind of a conceptualized example for a variant where it has allele A and allele T, and we have our cases and controls where I'm going to call y equals 1 or y equals 0 for a case and a control, and we can express the conditional probabilities in this table here. And so we can use those probabilities and plug them into this odds ratio to conceptualize our what the odds ratio means in this context. And so expressed here at the bottom is what we mean when we have what the odds ratio means in an association analysis, where it's kind of the ratio of the odds of an individual being a case given they're exposed to the risk allele A over the odds of you being a case given you're exposed to the non-risk allele T. So that's kind of what we mean, I think, when we're doing an association analysis and what the odds ratio means, but will that be particularly useful in trying to solve our problem? So the nice thing about the odds ratio is it has a mathematical symmetry to it in which we can kind of reverse the conditional properties and write it out in this way. And the nice thing about this form is that we can interpret the probabilities here as the allele frequencies of the risk allele within cases and within controls. So P1 is defined as the frequency of the risk allele in cases, and P0 is defined to be the frequency of the risk allele within controls. And so we can have this nice form here, or this nice conceptual reversed conceptual form for the odds ratio, which is just involves the allele frequencies of the risk allele in the cases and the controls. So why is that nice? Well, if we had individual level data, then we can just go away and estimate P0 and P1. Well, I mean, ignoring potential confounders, and we can just calculate by plugging P0 and P1 into that formula, and we get out what I denote throughout this presentation as what I call the true odds ratio, where if we were to know the perfect P0 and P1, then we could reconstruct the odds ratio. So you notice still here, we still have the question marks with respect to the linear model, and we notice that the logistic odds ratio does very well at estimating the truth, particularly when the effect gets small or is smaller. So this effect here is perhaps way out on the spectrum with respect to GWAS odds ratios, but we wanted to derive a kind of transformation that would work across a very large space of odds ratios. So hopefully that example there is a little bit edifying. So when I was working on this problem initially, I was doing it, I was ignorant of the historical solutions or historical attempts at kind of looking at this mathematical concept. And that's both dangerous in the sense that you could converge to one of the historical solutions, but it's also good in the sense that you ignore kind of what other people have done previously, and you might converge to a new solution. So luckily it was the latter, and not the first statement. So this type of model, and it seems a little bit crazy to want to try and apply the linear model for a variety of statistical reasons to a dichotomous outcome, but it has been used in econometrics and statistics quite a lot. And as stated in this nice text by Green on econometrics, it's not beyond redemption, which is kind of nice and makes us feel a little bit more easy about using the linear model to model a dichotomous outcome. So of course, like all good problems in statistics, Fisher has already thought about it and solved it in some sense nearly 80 or 90 years ago now. And it's interesting that he published this in the Annals of Human Genetics, which I thank actually a reviewer for suggesting a variety of papers in which I kind of trace back this historical fact. And he exploited the links between logistic regression and linear discriminant analysis to develop a prediction machine. So in that paper, he wasn't necessarily interested in the effects themselves. He was interested in doing prediction. But then Hagstrom, in an econometrics paper, went away and used Fisher's concepts and showed how you could kind of use his mathematical concepts to map the coefficients from analyzing a dichotomous outcome using the linear probability model to the logistic regression coefficients. So it's nice to know that it has this, people have already thought about it, and people who are much smarter than I am probably have already thought about it in quite a lot of detail, and that makes me feel a little bit more easy about the fact that we're doing some things like this. So also there's another path to a solution, and that this was developed by Press and Wilson when they were working for the Rand Corporation. I thought that was kind of interesting that within this kind of historical think tank, they were thinking about doing such things like this. And they used the reverse Taylor series approximation. So it's kind of doing a Taylor series around the logistic length function. And they initially wanted to do that because they were interested in providing good starting values for the iterative procedure for estimating the effects in logistic regression. So why that's important is that that is very similar to the actual well, if we fast forward to 2013 in a paper by the Annals of Applied Statistics by Pirinen and Donnelly, they kind of use a similar path to the solution to get out their own approximation. It was quite surprising to me that this kind of approximation already exists in the literature, and they were analyzing genomics data, and but their approximation is kind of buried in the text, and being in the Annals of Applied Statistics, it might be kind of outside the reader, the readership of most people in statistical genetics. And so they took this kind of first order approximation and they made it better by taking third and second order terms in the Taylor series. And they coupled it with some empirical testing, and you'll see in their kind of solution where this component here for their solution from the mapping of the effects from the linear model to the odds ratio. I think this kind of component comes from their empirical testing. So I wanted to put up the solutions to this problem by Fisher and Hagstrom, by Press and Wilson, and then Chang, who kind of formalized it for summary statistics, and then Pirinen's solution up, so that we could highlight that they seem to all be a function of similar things. So where beta here is the regression coefficient from analyzing the dichotomous outcome using the linear model, and the standard error of the effect here. N is the sample size, and P is the allele frequency of the allele that we're interested in analyzing. So you can also see that it's a function of K here, the sample prevalence, and pretty much Pirinen's is just is a function of the effect from the linear model, the sample prevalence, and so let's have a look at how well their methods work. So if we have the true odds ratio on this line here, and we can see that the work of Fisher and Pirinen works quite well at mapping it back to the odds ratio from the linear model. But as the effect gets larger, they seem to deteriorate, especially those first solutions that kind of aren't as good as Pirinen's. So in our paper, we kind of don't go any further with Fisher's and Preston-Wilson's solutions and just compare our method versus that of Pyramid. The reason being so is that it was found to be much better than these other two in all situations.
Sorry, Luke, can I chime in here? So
Sure.
are you saying it's a function of the effect size, or is it actually effect of the allele frequency? Because obviously your three SNPs differ in terms of their allele frequencies.
So you mean the mapping to the odds ratio
Yes.
being a function of the allele frequency?
Yeah.
So it's both a function of the allele frequency and the effect and the sample prevalence. So so here you can see that this is the regression coefficient from the linear model. This is the allele frequency of the variant, and this is the sample prevalence within that analysis.
Well, it's just my understanding was that those other transformations broke down most when the allele frequency was small.
There is a kind of a relationship with the fact that when the allele frequency is small, the effect tends to be large.
Yeah.
That may well be the case, but I suppose this conceptual example is a little bit dangerous to look at and infer things but across the whole spectrum of effect sizes, these transformations broke down very quickly in comparison to this one. So I wanted to give a broad intuition to the path for our solution. And so as I stated earlier, if we have individual level data, then we can just observe P0 and P1 and plug them into the odds ratio as a function of the allele frequency within cases and controls. But if we don't have individual level data and we only have summary statistics, then can we reconstruct P0 and P1 from the observable things that we have? So what do we have? What are the observables that we have at our disposal? We have this big K, the lifetime probability that an individual will be affected by the disease. We have the sample prevalence K, which may not represent big K well, especially the reason being when you oversample cases relative to controls, then little k deviates quite substantially from big K, depending on how the study is designed. And you have the allele frequency of the risk allele or effect allele across cases and controls. And we have the regression slope coefficient from the linear mixed model or the linear model and its standard error. So you may have some of these, not all of these, and we provide a whole variety of assurances and transformations depending on whether you do or don't have some of these components in of the summary statistics spectrum. So we've already kind of introduced this concept of modeling Y here, this random variable, as a linear model of the SNP X, but I thought I'd just write this out formally. And we kind of consider Y here to be a Bernoulli random variable and X here to be random, which is not always the case in, well, classically not the case in regression to assume that X is random, but in this case, we don't necessarily exploit that concept in the least squares type solutions, but we exploited it in the mathematical relationships that we go on to derive. And so that's just an introduction into what the model kind of looks like and what our assumptions are. And then the concept, the intuition for the solution is that we're interested in reconstructing P0 and P1. And so it's kind of the classic high school mathematics problem where you have two unknowns, and if you can set up two equations that relate the things that you know to the things that you don't know, then you can back solve for the things that you don't know. So provided you have sufficient information. So we set out to set up such a set of equations, and we can look firstly at the allele frequency P, so the allele frequency of the risk allele A, and it turns out because Y, the phenotype, partitions the space completely, you can use the law of total probability to write out the fact that the allele frequency is this weighted sum of the allele frequencies in control and the allele frequency in cases, and it turns out the weight is well, the probability that Y equals 0, which is 1 minus the sample prevalence. So we also know the form for the regression coefficient from the linear model, which is just the covariance between Y and X divided by the variance. And we can go away and derive underneath the assumptions of the previous slide, what the covariance between y and x is. And you can see here it's going to be a function of P1 and P0. So that gives us the numerator. We're interested in finding the denominator, and we can go away and do some more algebra underneath kind of the assumptions of well, statistical theory and derive this form for the variance. And you'll notice here that the variance of x given y equals 0 and the variance of x given y equals 1 is not an observable concept, or not an observable form from summary statistics. So we're going to need to assume something about the form of the variance within cases and within controls to get at these, or to kind of plug in and get a solution. Initially, when we were deriving this, I was under the impression that we only use the assumption of Hardy-Weinberg equilibrium within cases and within controls in this step here, but implicitly we've used the assumption that the genotype frequencies within cases and within controls are in Hardy-Weinberg equilibrium to derive this component and this component. So that assumption's already implicitly in there, but we can do some, you can break the rules mathematically in it as long as it works. It's not a complete breaking of mathematical principles. So like I said, we have this form for the variance, and we're going to have to, given we have summary statistics, we're going to have to assume something to get at the things that we're interested in. So we can assume, what I'm going to write here is assumption 1 and assumption 2. We can simply assume that the variance of x is equal to what most people will think about it as 2p times 1 minus p, or we can make this second assumption where we assume Hardy-Weinberg within cases and within controls. So which assumption is better and which works? I was always under the impression that this assumption would be a better assumption, but that may not be true depending on how the genotype frequencies may diverge from Hardy-Weinberg for a whole variety of reasons. So we won't go too much into that. So here's how kind of we solve it, and it kind of seems trivial once you do it. We just plug in the form for the covariance and the form for the variance in this expression, and we rearrange for P1, and we know that we know the form for P, and then we can just rearrange that and plug this P1 into here and rearrange, sorry, I actually plug P0 into this equation and rearrange for P1. This right-hand side here, you can see is just a function of K, P, and beta 1, the things we know from summary statistics, so we can reconstruct P1. Then I can plug it in here and reconstruct P0, and then I have all the information I need to plug it back into that odds ratio in equation 1 from the slides earlier.
Yeah, 30 minutes left, so speed up.
Okay. So here's the form once you plug it all in and rearrange and do the algebra. And you can just do the exact same process and that I did earlier, but plug in the second variance assumption here and rearrange everything and get out this solution. So this solution is not kind of what I thought it would be, but it is what it is. And so here we can see that this is actually a solution to a quadratic. So that's kind of perhaps troublesome in some sense, but I mean, perhaps that's a better approximation to the truth. So plugging those things into our simulated data kind of example, we can see how well our transformations were. So odds ratio 1 and odds ratio 2 are those derived under the two assumptions. And in the brackets here, you can see the absolute deviation of this from the true odds ratio. So you can see that OWLS does a little bit better than Pyrenees. Of course, logistic regression is a little bit better still. And as the effects get small, the deviation gets very small. So it's a little bit dangerous to, just from these small conceptual example, to assume that your method works well and does it work well across a lot of different situations. So we went away and did a whole variety of simulation studies to try and test the transformation. So the first simulation study we used, and in all of these simulation studies, we use real genotype data to simulate the the phenotype. So we used the JIRA study for the genotype, and we had 1.1 million HapMap3 SNPs, and we subsetted the JIRA cohort to 10,000 individuals. And using this real genotype data, I simulate 50 case control phenotypes under the logistic regression model. So the phenotype the data generating process can be assumed to come from a lot of different models: Probit, logistic, the liability threshold model. But in this scenario, I used the logistic regression, and I included one PC, or the top PC from the genotypes, to mimic population stratification. So underlying the phenotypes are 100 causal variants. The reason why I chose 100 was that I wanted the effects to be large and detectable. And in this case, it just turned out that the sample prevalence was 0.5. So I analyzed the simulated phenotypes using logistic regression with PC correction and Plink, and the linear mixed model in GCTA. In the second simulation, we used real genotype data again from the UK Biobank, and we took the set of, this was before the second release, and so we took the set of 140,000 individuals, which included relatedness, and the same set of HapMap3s as in simulation 1. So for each of the 5 scenarios, well, I'll get to the 5 scenarios in a minute, we simulated 50 case control phenotypes using a different subset of 10,000 individuals for each replicate. So the reason why I left related individuals in there is I wanted to try and mimic cryptic relatedness, as in when we sampled 10,000 individuals from this larger set, then we probably get some related individuals within the data. So that kind of is good for the linear mixed model. And so these 5 scenarios, I varied kind of the properties of the liability threshold model, and we can do that in GCTA. And so I varied the population and sample prevalence to kind of mimic different levels of case ascertainment and different levels of how rare the disease is. And again, I had 100 causal variants. So I used the logistic regression and the PC correction in Plink 2 and the linear mixed model in GCTA to analyze the data. So just to kind of go over the simulation scenarios under the liability threshold model, here you can see a variety of sample population prevalences getting rarer and rarer. And I oversample cases such that I can get these sample prevalences here. And I also vary the heritability to try and perhaps mimic something that looks a little bit like schizophrenia. In the final study, I only used rare variants because we were a little bit unsure about how well the transformation would do if you just looked at rare variants, and we looked at this map spectrum here. And I wanted to really kind of test the method by oversampling as many cases as I could in the UK Biobank, and that's where, so this is kind of the maximal amount of cases that you could sample or oversample in that bigger UK Biobank data set. So I'm going to run through the simulation study results, and this is one way of visualizing the results. And so here on the x-axis, we have the true odds ratio, and you can see it ranges from 1 to 10. The reason why it starts at 1 is that I transform everything onto the risk allele. Otherwise, you compress the space between 0 and 1, and it's a little bit misleading. And on the y-axis here, I have the estimated odds ratio for logistic regression in green. So the green line is the fitted linear model to the points. I have in red here our transformed values, and in blue the transformed values from Pyranin's transformation. And so each point here, there's 5,000 points on each plot, and each one represents a simulated effect and its kind of estimated effect on the y-axis. So we kind of summarize how well the model does by looking at the adjusted R-squared and the slope. The closer these things are to 1, then the better the hypothesized performance of the method is. And so here, this is the results from the first logistic regression in the JIRA data set, and here the liability, the first liability threshold model simulation. And so there's not going on, you can see, we can skip through to see that the different liability threshold model simulations, the results themselves don't change a whole lot. The slope and adjusted R-squared is usually very high, and it appears that Pyranin's method tends to systematically underestimate the effect once it gets past kind of 2.5 to 3. you will also notice that maybe the variation in our method gets a little bit larger as the population prevalence gets a bit smaller. That might be a little bit misleading. Well, I mean, there's lots of reasons why that may be, but on average, if we look at these results, it appears that the transformation is working very well, and it starts to deteriorate a little for those effect sizes that are way outside the GWAS kind of spectrum, but you may have such a scenario where you get a true odds ratio that large potentially. And so in this final one here, you can see that in the rare variation, it seems to work quite well. So that was a little bit surprising to me, even better than kind of what's going on in this scenario. Exactly why that is a little bit difficult to disentangle. But I was kind of satisfied that it kind of works. It works reasonably well for this in this simulation scenario for rare variants. So of course, that's in simulated data. What does it look like in real data? So we just took the type 2 diabetes phenotype from the UK Biobank. Why do we do that? Well, it's a monitoring, reasonably heritable trait, and it's well studied. And so, there's some reasonably large effects. And so we took a subset of just unrelated individuals from the UK Biobank. The reason we did that is so that we could, because we don't know the truth anymore, we wanted to have a benchmark, and that benchmark was going to be logistic regression with PC correction. So including the relatives would be a little bit unfair to the logistic regression analysis. And so here you can see the sample prevalence in for type 2 diabetes in the UK Biobank, and we analyzed 1.1 million HapMap SNPs using bulk LMM and Plink2, corrected for these covariates. And so here we can see the analysis. On the left-hand side is the result from our method, and on the right here we see the results from Pyrenees. So not a whole lot of difference between, well, there's no difference essentially between that of our method and that of Pyrenees. So it's up to the user as to what your preference is. I mean, obviously we'd advocate for using our method for a variety of reasons. So that's all well and good, but in the actual manuscript, there are a lot more simulations and a lot more visualizations of how well the method performs in summaries in simulation. So what other assurances can I give you about how well this method is going to work? So as we kind of touched on before, the odds ratio solution to a quadratic, and quadratics can have 0, 1, or 2 solutions. And so given that, I wanted to give the reader or the user some assurances as to when you're going to get 1 solution, when you're going to get 2 solutions, when you're going to get no solution. And so in the manuscript, I derived the actual bounds, which are a function of beta, k, and p, as to when the transformation will break down. So you kind of know before you plug it into the transformation when this transformation will break. It turns out that it's actually very hard to break the quadratic property in the sense of getting no solution. And for pretty much up to odds ratio of 50, there's always a single solution. And only once you kind of really twist the parameters that you'll get some either 2 solutions or no solution. No solution to me kind of feels like there's something potentially wrong with the analysis or the data. So that might be telling you something. There are other transformations out there where it will always give you a solution, but I'm not necessarily happy with the concept of always giving you a solution when actually the data are telling you that there's a problem with the effect. We also investigate if you didn't have the allele frequencies, how well does our transformation work if you just plug in the estimates of the allele frequencies from the 1,000 genomes. So we plot kind of we do all the simulations with that assumption again. If you don't have an allele frequency, we also derive consistent transformations using the standard error. So you might imagine that you don't have a good allele frequency reference, and so you might have the standard error of the effect. So you can actually get at a transformation that's equal to the OR1 and OR2 by using the standard error as a replacement for the information of the allele frequency. But we prefer the allele frequency one because the standard error estimation can be a little bit wild for different reasons in the linear mixed model, usually for extreme cases. So we also show when the variance assumption A1 are kind of maximally different. So that's kind of just a mathematical property. We also investigate the breakdown of the method for deviations from true K and P. And we also investigate our Hardy-Weinberg assumption. So inside the Hardy-Weinberg assumption is a lot of different concepts. And there's lots of reasons why Hardy-Weinberg can kind of break or deviate. That's kind of also linked with the fact that we're using a linear model to kind of model probabilities. And we also provide a standard error transformation. So that might be useful for people doing meta-analyses. So what are the caveats of the method? Well, some of the ones that I'm going to highlight here are just not unique to what we're doing here. They're unique to applying the linear model to dichotomous outcomes. But it's important to kind of highlight this, that implicitly that the linear probability model assumes that the error is heteroscedastic. And so you can kind of go away and read why that is. But this was also highlighted by Chen et al. In the American Journal of Human Genetics, where they looked at population stratification generating really kind of playing with this heteroscedasticity under the linear mixed model and giving you poor p-values. So another problem of the linear model is it gives you no assurances that the predicted outcomes will look like probabilities because they're not constrained to lie in the 0-1 space. So that was kind of the motivation for why logistic regression was invented, is to kind of constrain the predicted probabilities to lie within the 0-1 space. That might not be such a problem, but we can see that, you'll see that in the response in the next slide. The odds ratio transformation also based on linear regression on genotype, and then we transform it to the odds ratio for alleles. So that's conceptually kind of interesting whether those things are kind of equal. But the additive risk model may break down for a variety of genetic and non-genetic or data kind of extreme oversampling of cases, for example. So it's all tied up also in our Hardy-Weinberg equilibrium assumption. But in this final kind of caveat, there's a lot of things going on. But this kind of doesn't happen for most effects within most GWAS range of effects. So in reply to the first heteroscedastic problem, I mentioned Chen, and we did use Chen's method to kind of investigate how well it estimates the effects and how fast it was. And it's quite fast for estimating score statistics and p-values, but quite slow at estimating effect sizes. So that's kind of counter to what we're interested in doing in our manuscript. And so we did try. So the unrestricted prediction domain may not necessarily be a problem, but the important thing to highlight is that if the predictions that we make from our transform odds ratios, well, we shouldn't really be using it as a prediction machine because we're just interested in estimating effect sizes. But if you were to kind of look at the predictions and there were a lot outside of the 0-1 space, then you might question whether the linear probability model is a good model for your data. And we also show the limits. So we do a lot of simulation work to kind of try and break our Hardy-Weinberg equilibrium assumption, and the reader can actually feel the space of when things are really going to break down. So hopefully that's kind of satisfying in some sense. So why should you use our method? I kind of showed that Pyranin's method systematically underestimates the effect sizes across all the different simulation scenarios, and I expect that to happen in real data, although you saw in the real data example that it didn't, but that was because the effect sizes themselves weren't that large, but our method gave the exact same answers. So the one thing I do like about our method is that we invoke statistical genetics theory rather than kind of using a Taylor series approximation around the logistic link function, which kind of has no connection to statistical genetics. And so from that perspective, I feel it's more complete. And we have tested the limits of the kind of method quite substantially, and we try to give her a lot of assurances and constraints on when our method would break down, and so hopefully, that's satisfying for the reader. So in conclusion, given the ever increasing sample sizes in biobank data, we believe that linear mixed models are probably here to stay for at least some while. They may, analyzing dichotomous outcomes using generalized linear mixed models may come online. But I mean, the linear mixed model is always going to be ahead of the generalized linear mixed model in computational efficiency. So people interested in analyzing those data are probably going to always reach for the linear mixed model first, at least. And so the new paper by Poru Lo kind of has a look at that and using the linear mixed model with relatives in the data to try and maximize your power. And so we don't kind of advocate for using the linear model in all situations for dichotomous outcomes, and we think that logistic regression should remain kind of the norm. But I mean, obviously that's up to the researchers themselves. And so our final statement is that transformations improve comparability results from perspective and already performed mixed models by providing a common comparative scale for the genetic effects. So this is kind of nice in the sense that if you've already performed a GWAS or is in the historical summary statistics literature, you can kind of pull out the effect and compare it to your effect. And we also have a Shiny app which will do the transformation for you, and you can download an R function and just use it in your day-to-day workflow. So it'd be great if people are interested in this method to actually do that and test it. And if you're interested in the method, read the paper that's coming out in genetics in the next few weeks. So I'd like to acknowledge everyone in the group here and for their sharing of the problem and the discussion, the funding bodies, and for those data providers for providing the data. So thank you.
Great, thank you very much, Luke. So can I open it up for questions? Just unmute yourself if you want to ask while you're thinking. I'll ask the question. So Luke, if people do a logistic regression and a linear mixed model on the same data, how do the p-values for association of the SNPs compare?
I think for most effects in the GWAS, range between like 1.1 to 1.4. I mean, I haven't looked at that extensively in simulation, but I feel that people feel like they're about the same. I did do some investigation, and the p-values look very similar, and you'll make most of the conclusions, you'll make correct conclusions most of the time. But there are a lot of papers coming out now telling you kind of why sometimes the linear model breaks down and gives you incorrect p-values for a whole host of statistical reasons and potentially data reasons as well. So I wouldn't go and say everyone should use the linear model and the p-values will be correct always. So that would be my final opinion.
So, so has anyone got a question? So I'll just give you some context of why Luke's method came up recently in debate. So Jerome's group and Andrew McIntosh's group have been using UK Biobank. And with the UK Biobank data, because the sample size is so large, it seems to make sense to use a linear mixed model to take account of all the cryptic relationships between individuals. And so that's difficult then with the logistic regression. And BGenie is the method which is from Jonathan Marchini's group, which is being kind of marketed with the UK Biobank. And in that software, there's a correction made for covariates. And so then you're doing a linear mixed model on a covariate corrected phenotype. So then the 0-1 data start looking like, a bimodal distribution of little effects deviating from 0 and 1. And so the discussion was, how do the estimates from using BGenie compare to a standard logistic regression, which of course, as you might know, is very slow when you've got covariates in. And so the comparison was that the p-values were very similar. And then when using Luke's correction, the odds ratios coming out of the analyses were the same. So it was a good confirmation that using BGenie on the 0-1 data corrected for covariates was robust. Any other questions?
Yeah, I've got a quick question about the simulation. So this is Raymond Walters from the Broom. So in the simulation that included effective population stratification, I'm curious, like what ranges of effect sizes for the population stratification you looked at? Because my expectation is there's at least some impact here in terms of to the extent there's population stratifications, you get a difference between what the logistic regression odds ratio is and what you're calling the true odds ratio, just based purely on the case control allele frequencies. So I'm curious, like as population stratification sneaks in, how that affects the efficiency of the conversion.
Right. So with regards to how much variance the PC kind of explained, I think we did look into that. I think I estimated the effect for the PC to be quite large, and they explained maybe like 10% of the phenotypic variance on average. And it is kind of difficult to characterize when you have a large kind of covariate effect, how that affects how well you can get back to the true odds ratio. And in the actual manuscript, we did a bunch of simulations where you simulate a very large sex effect, for example, and we have a very large, in the sense of explaining a lot of variation, we have a very large genetic effect. And we saw that both logistic regression and the linear model transformed odds ratio from the linear model broke down at varying rates depending on how much variation the genetic effect explained. So does that kind of, because I know in logistic regression, depending on one of the properties of logistic regression is that the effect can change depending on how many, on what covariates you fit in your model. And so I think we're interested to see how logistic regression works when you have a very large covariate effect or sex effect, for example.
Great, thanks.
So, hi, thanks. I have a question. So I've previously published a paper on the underestimation of effect sizes in logistic regression analysis. So if you have multiple SNPs that influence a phenotype, then the effect sizes are underestimated because of the non-condensability.
Is that?
And I was wondering, if you use a linear model, is there any chance that this problem is also solved?
I think is that Eska? I think
Yeah,
I have,
yeah, hi. Yeah, it's taken by my student Springer. He's the first author on the paper.
Yeah, yes, I have read that paper, and is that kind of linked with Simpson's paradox in a way?
Yeah, yeah, exactly.
Yeah, it's kind of I didn't explore that concept that deeply, but it is discussed in the discussion. And, you would hope, I was hoping that it would solve such a problem, but I didn't look at it in that much detail. And so, it would be nice if the linear model was kind of a solution to all our problems with respect to that concept, but at this stage, I'm not sure as to the limits of how well it goes about solving that problem.
Okay, so in your simulations, did you set up like a single SNP influenced a single phenotype?
Yes, we did. That was in the set of simulations. Yeah.
Yeah. Okay. Yeah. Thanks. Well, maybe that would be interesting to look at in the future then. But thanks. It was a great talk. Very clear.
All right. Thanks, As.
Anyone else? No. Okay, well, the hour's nearly up anyway, so just leave me to thank again Luke for giving a very clear talk and for jumping in at the last minute for us. And really to say, yes, please let me know if anybody else would like to make presentations throughout the year, or if you've got ideas of talks that you'd like to hear. I think it's good that we have talks like this, which are kind of, quite detailed and actually you know, at the cutting edge of what we're doing when you've got real problems with real data. So if you've got ideas, please let me know. Okay, with nothing else, we'll say goodbye.
Thank you.
Okay, thanks. Bye.
Thank you.